Okay, in this video, we're going to talk about center of mass and how to calculate it algebraically. We're not into the calculus version of center of mass yet. That'll come later in the year. But just the algebraic formula for the center of mass and then applying it to this problem number 5 in the problem set. And if you don't have the problem set in front of you, I'm going to explain the problem. You'll be able to see it and see how we solve it. So first of all, here's the formula for the center of mass, right? And we can write it kind of like this, xcm. So what xcm means, again, is the x coordinate of the center of mass. When we do center of mass, like so many other things, we have to separate all the dimensions. So we take care of the horizontal dimension, the vertical dimension, the in and out of the paper dimension. If it's 3 dimensions, we treat each dimension separately. Okay, and so it's the x coordinate for the center of mass is 1 over the total mass, okay, the mass of everything in the object, and then times, and what we do is we take each individual mass. So if it's made up of a bunch of things, like this problem is 3 cubes, so we'll take the mass of each cube and multiply it by the x coordinate of the center of that thing. So you break it up where you know the center of each thing, the center of mass of each thing, the mass, and then you're taking those products and adding them all together. Right. Notice that when it comes to the units here, the mass cancels out. What we have is 1 over kilograms times, and then out of the parentheses we're getting kilograms meters. Those are our standard units. So the kilograms cancel out, and we're just left with meters, which is what we want, right? We're looking for an x coordinate, so that should have the unit of meters. What we're going to look at now is this problem. So what we're looking for is the center of mass of this object, or this collection of objects. What we have is 3 cubes. They're all the same density, and we're looking for the center of mass of this system of the 3 cubes. Now, we always look for symmetry when we can, and we use it to our advantage. So in terms of the vertical, up and down, and in terms of the front to back, the center of mass of all of these are in the same location, right? Vertically, it's here. It's this kind of dotted line that we can see. That's the center of mass. So we don't have to worry about that. It's not a separate calculation. And then all of these are also, right, they're lined up along the same center. And so even front to back, they're all kind of at the same location. You would just take the center of each cube, which again would be in the same place. So we're not trying to figure that out. Our main concern is finding the center of mass of this whole system, right? In terms of the left to right, the horizontal axes. Our first thing, right, in the formula, we're trying to find the total mass. So the first thing we have to do actually is find the mass. Right? Well, how do we find the mass? The way the problem is laid out, here's all the given information. There's no mass. So what do we do? Well, what we can do is, since it's the same, they're all the same density, they're all the same material, whatever it might be, we can take L and use L as a way of representing the mass, right? So L cubed, this one here, the first one, is going to have L cubed. So whatever the density is, right, if I take a certain volume, then that represents a certain amount of mass. And that's going to be directly proportional. The mass is going to be directly proportional to the volume. So L cubed is what I use as the mass for that cube. Plus, and then it's going to be 2L cubed. So this is going to be 8L cubed. So what that means is that if you double the length, now you have 8 times the volume. That means 8 times the mass. Okay, and then plus 3L cubed. Parenthesis, cubed. So this is plus 27L cubed. So we add all that up, and we get 36L cubed. This is an expression of the mass. Okay, it's proportional to the amount of mass that's there. So this is what I'm going to use as my big M, the mass the total mass that goes in the denominator of that formula. All right, so now I can kind of start writing out the formula. So X, center of mass, is 1 over, I'm just following from the formula, so 1 over m, 36L cubed. Now I need to find the x coordinate and the mass of each of these cubes. The real trick now comes in choosing your origin wisely to minimize the amount of work for yourself. And so what I'm going to do is I'm going to choose the center of the big cube as the origin. All right, so here's 0, and you can imagine, right, all the dimensions coming out of here. And that means that, but I'm gonna treat the left as the positive direction, right? And so here's the center of this cube, and here's the center of this cube. I just have to find out those coordinates. So how far away are these, right? So if this is this, so what the coordinate of the center of the big cube is just 0. That's the origin. So the big cube, going into the formula here, x, the x coordinate is 0. That's really nice because now, 27L cubed, which is the mass of that big cube, that goes away. It's 0. So notice I chose that at one of the centers. I chose the origin to be one of the centers so that I can eliminate one of the terms in the parentheses. Anytime you can do that, do that. Right? It comes in really handy too when it gets to things like calculating torque, moments of inertia, things like that in rotation. So the second cube, where is that located? Well, the distance from the center to the edge is 1.5 L, whatever L is, right? We don't need to know. And then from the edge to the center of this is 1 L. So the coordinate, the x coordinate, remember I'm making to the left, positive. So this way, that's my positive x direction. So the x coordinate of that other cube, the middle-sized cube, is 2.5 L. And what's the mass? 8L cubed is the mass. Now the tiny cube. So now from the middle of that cube, the middle cube, to the edge is another 1L. And then from the edge to the middle of the little cube is 0.5 L or half L. So now this comes out to 1, 2, 3, 4 L. Okay, so the x coordinate there is 4L times, this one's just L cubed. Okay, and when you do this algebra, this arithmetic really at this point, notice all the L cubes cancel out, and the center of mass turns out to be 0.67 L, or not all the L's actually. You have the L cubes, but then it's kind of like these L's stay there. That's it. I don't have any other particular units. I don't know if it's meters or what it might be. But we've got to realize that this is a coordinate, and this coordinate is to the left of the center of the big cube. Right, to the left of center of big cube. And then if you want to find the center of mass in relation to any other part, then you're just doing a little bit of quick arithmetic, right, to figure out how far it is from any other location. But again, because I chose the origin as the center of the big cube, that's what this means. So the center of mass is 0.67 L to the left of the center of the big cube. So I hope this helped with your understanding of center of mass and how to solve a problem like this. Remember, every dimension you have to keep separate and choose your origins wisely. Thanks for watching. Don't forget to like and subscribe.